Shall I start? Right, guys, have a sit and let's continue. So we derived or rather re-derived, it was derived by Rayleigh and Fjortoft, two algebraic conditions which are quite universal. You see that the value of these conditions is in that you only need to look at the velocity profile itself to tell whether it is stable or not, or at least make some assumptions about or some conclusions about whether this is observable or not. So that's why it is so powerful. These results are so powerful. You don't need to do any computations. You look at the picture and you make a conclusion straight away. So that's what the value of these results are, and that is the reason why they have names attached to them. What I usually teach my students is that if you see a theorem or mathematical statement or formula or anything with the name attached to it, it means that it is very non-trivial, very versatile, very useful example, or a formula or theorem or result. And it means that it is non-trivial to prove it. It might be very trivial to use it. It might be very easy to use it, but it is very non-trivial task to derive that and prove that this works. And we spend quite a lot of time on doing that. Even though we were just repeating, or I was just repeating what was very well known for more than 100 years. Still, it took us quite a long time. All right, so these are the two results. So we need to make sure that the velocity profile has inflection point where the curvature changes. And in addition to that, we should be looking for the satisfaction of this condition. So second derivative times difference of velocities has to be negative at least somewhere. If it is non-negative everywhere, forget about it. So I spent some time drawing these sketches here. And what I would like to do is to just go through them one by one. So what you see here is velocity profile as a function of z. Remember, we consider the two plates. This is bottom, this is the top, and there is some sort of velocity distribution between them. So that's why I have u along the horizontal axis and z vertically. Okay, so that's how fluid would flow. So what can you say about these two? So which criterion would you use to assess the stability of these sort of profiles? So we have two. One is Rayleigh, the other one is Fjortoft. So I just inverted them. So they gave them here in opposite order. So these are the two conditions. What can you say about these two? So first, you are looking for what? Just graphically. Inflection point, right? Do they have inflection points? No, the curvature is the same. So therefore, that's it. You can say that these profiles, they cannot be unstable, whether it is good or bad. So from a mathematical point of view, it's probably bad because it is of no interest to mathematicians. From a physical point of view, that's exactly what you're looking for. So these can exist. If you can create them, then they will be there for you. Experimentally, you will be able to see them. Okay? All right, so in this case, u double prime bar is equal to, well, rather not equal to, but what can you say about the sign here? Second derivative is positive? Negative? You sure?
What they did it.
All right. So really, that's how you put it. Z is this way, so therefore you're covering Z direction, right? So it is like that, right? So if you turn it around, it will be like that. So it is negative, right? So, and it is always negative. It doesn't go through zero. What about this one? so it is similar, but in this case it is positive. So it is like that. So you turn it like that, and it is positive, right? So all right. So therefore, stable by Rayleigh. What about this one? What can you say about Rayleigh? So yes, inflection points are there. So that's one of them. That's the other one, right? That's where the curvature changes. Right? Okay. So by Rayleigh, it can become unstable, so therefore you might or might not be able to see them. But what does Fjortoft say? So, what do you think? Now we need to be a little bit careful here. So, first of all, the way to answer that question probably is best not in this diagram, but draw the diagram slightly differently. So you can probably see what I mean here. So you can easily say that the inflection point there or not. But if you are talking about Fjortoft's condition, this one, well, unless you do it every time for breakfast, you probably will have some difficulty doing that, right? So just remembering what needs to be done. So especially when you do it for the first time, so probably it is not that obvious. So therefore, I suggest that we just do not look at these pictures, but rather redraw this diagram in somewhat different but equivalent way. And this is done on the next page. So this is now like a vertical channel. So Z in this direction, so one plate is here, the other plate is here, so we turn the channel to be vertical. And the velocity profile is like that. And that is inflection point. Okay? So what is then suggested to be done is that rather than having this plot U of Z, we shift this by the quantity corresponding to the inflection point. So this is inflection point, and this is how high it is above the Z-axis. So we will push it down, so this point slides to that point. So therefore, we are really plotting this, U minus U sub S. Why? Because Fjortoft's condition is d squared U bar multiplied by U minus US. Agree? So therefore, by looking at this picture, we can see clearly where this is positive and where it is negative, right? Here it is positive, here it is negative. Right? Okay, so, all right, if we look at this picture here, so clearly the second multiplier here is positive, here it is negative. And here it multiplies by the second derivative, and the second derivative here is positive or negative? Negative, and this is positive. So this product here is negative. What about here? So we have this to be negative and this to be positive. So what can we say about this overall? It is always negative. Inflection point is there, and this is also negative. Both conditions are satisfied. So therefore, you do not really expect this to be seen, right? Because the perturbations will kill this. Okay? Good. So another example. So a very similar picture, but now I inverted. So again, I have my U of Z profile shown here. And I have my inflection point, which is just here. And then I shift it up. So this is still U minus US, but because US was negative, so it is essentially by subtracting negative quantity, we're pushing it up. And it will look like that. So clearly, then this difference here is negative, here it is positive. So what can you say about this? The product. So it is positive, and this is positive times negative, negative. What about here? So this term is positive, this term is negative. So therefore, positive, negative, or negative, positive. Overall, it is still, product is negative. So therefore, what can you say about this? Well, most likely we will not be able to see that. Okay. So, now I will, what else do I want to do? Well, what about this one? Same idea. So this is my u. This is my u minus us. So this is pushed down so that it is now here. So what about this condition? So first of all, obviously, inflection point is clearly there. So, but here we will have the second term, which is positive. And the first term is positive. So positive times positive, so therefore this is positive. Okay? And what about here? So this is clearly negative, this bit is negative, and the, so negative and this one, negative. Negative times negative. So here it is positive, what about here? So the conclusion? So this is probably something which we will be able to see. Okay? So that's how easy it becomes. So derivation is very difficult, or lengthy, I would say, not difficult, but lengthy. But once we made the conclusion, so the qualitative conclusions after that are very simple. Now, let's go to this picture. And that is a little bit tricky. So, I already shifted it somehow, so that's my inflection point. Right, so it is a little bit, so I'll just do it like that. So my inflection point, it is on the axis, so I didn't draw the u of z, but rather u minus us of z straight away. So that this inflection point is straight on the axis. All right. Inflection point is there. Rayleigh is satisfied. Okay, so inflection point is there. Rayleigh is happy. Fjortofts. So we have multiple regions now. We have this region, we have this region, and this region. So we have 1, 2, 3, 4 regions. 4 regions as far as this is concerned. So what can you say about this between the between this line here and this point here? So this term here is negative. What about the curvature? Negative. So therefore the product positive. Let me put it here. So this is positive. What about here? So this is positive. This is, so overall the product will be negative, right? Let's go to this one. So the second term here is negative. Curvature. So curvature is positive. The quantity is negative, so therefore the product is going to be, what is it? Negative, right? And finally this region. So clearly the second term is positive here there. And what about the curvature? positive. So therefore, this is positive. So positive here and positive here. Negative here and negative there. So we do have regions with negative. But do you think it is enough in this particular case to make it unstable? So now let's go back to the derivation. The derivation requires us something to be negative. But that something is not the quantity, not the function, not the value of the function, but rather integral itself has to be negative. Agree? So integral has to be negative. Integral is essentially the area under the curve. Right? And we said that for area to be negative, potentially be negative, we have to have function that it is negative. And we do have regions where the function or the product that we consider is negative. But what we need to make sure that the whole integral remains negative. And unfortunately here it is not negative everywhere. It's negative only over this region here, but this and these regions, these two regions, they have positive contributions to the integral. So we have regions which contribute to the integral negatively, and then we have regions which contribute positively. The question is, who is going to win? If it is everywhere negative, we know. If it is everywhere positive, we know. But if it is partially negative, partially positive, who is going to win? So, really, you cannot say that. So it looks like in this case it is more positive than negative, right? Because this area plus this area, overall this is more larger area than the area negative area in these two regions. So even though we do have regions where the Fjortoft's condition is satisfied, we need to keep in mind that it is ultimately, it should be the integral itself that must become negative. And integral will contribute, will have contributions from different regions between z equals minus 1/2 and z equals 1/2, right? And we have to make sure that overall contribution remains negative. All right, so let me rephrase that in simpler terms. So the condition is that the integral must be negative. For integral to potentially be negative, we need to make sure that the function which we integrate is at least partially negative. If it is completely negative, then definitely the integral is negative. But if it is partially negative, it does not mean that the integral is going to be negative. And that's the example, graphical example of that. Is that clear? So because of that, both Rayleigh condition and Fjortoft's conditions, they are so-called necessary conditions for instability, but not sufficient. It's not sufficient for Fjortoft's condition to be satisfied for the flow to be necessarily unstable. It might still be stable. And that's the graphical qualitative example of that situation. On the other hand, if Fjortoft condition is not satisfied, then it is safe to say that the flow is stable. So if the Fjortoft's or Rayleigh conditions are not satisfied, at least one of them is not satisfied, we safely say that the flow is stable, and we can see that. On the other hand, if Fjortoft's and Rayleigh conditions are satisfied, it is not guaranteed that the flow becomes unstable. And that's the example. Is that clear? Okay, so please keep this in mind for the future. Okay, so Now, next question is, if the situation is really like that, what do we do? And we still need the answer, definite answer. And in this case, unfortunately, we have to go the full length. We have to find the formal algebraic solution. No other way. So we need to solve this equation. So, and I'm talking about this equation. We have to solve it. We have to solve it. We need to find this sigma, and we need to decide what actually that sigma, the numerical value of that sigma. If it is positive, if sigma are positive, then we have an instability. If it is negative, then we have stability. So that's how far we went. So we did a lot of work. We were able to come with a very diverse and versatile qualitative criteria, but unfortunately the situation is such that in some cases qualitative consideration is not sufficient. And that's what I will try to show you next. So specifically what I will do, I will consider an example where none of these criteria that we just worked through are going to work. Why? Because I will choose the situation when the profile, velocity profile, is given by linear combination of linear functions. So nothing prevents me from choosing the linear profile. So we have some sort of linear segments joined together, and therefore what will happen with this equation is if a base flow consists of linear profiles, what will happen to this equation straight away? Can you see what happens? So if the profile is linear, what happens? So what happens to this term? It goes away. So therefore, all this is gone. So we are only left with this. And it is a product of two terms, and this, of course, will have to be equal to 0. So therefore, either this is equal to 0 or this is equal to 0. Can this be equal to 0? No, so therefore, this must be equal to 0. But this is a linear equation, and these are the conditions for linear equation. What is the solution of linear equations, homogeneous linear equation? So therefore, it is linear equation with a 0 right-hand side and 0 boundary conditions. What is the obvious solution for this system? 0. Trivial solution, right? Trivial solution. And if it is a linear system of equations, you solve it, you get a solution, and that solution satisfies boundary conditions. According to uniqueness principle for linear equations, that's it. There are no other solutions. You cannot find anything else. So unfortunately, on the surface, it looks like we will end up with a trivial solution. Okay? So if it is just a straight line from one wall to another, then no perturbations are possible. So it will be stable because nothing, you cannot really perturb it in any way. That's what that is. So, but I will make your life a little bit harder by saying that I don't really have purely linear profile, but I have the profile which looks like that. So I'll say example. So, and I draw the sketch. So, two coordinate lines So what do I have here? This will be my u of z bar axis, and I will make the numbers a little bit simpler. So this will be 1, this will be 1, this will be minus 1, this will be minus 1. So this is the velocity profile I would like to consider. It is called mixing layer. And what is that mixing layer? So what is the... It is a prototype of an actual physical flow, which is observed in nature, and I will show you the actual pictures of that once we solve the problem. So you have two jets. One goes from left to right, the other one goes from right to left. And at the border, they somehow transition. So that's what we have here. So this is a jet which blows, or wind which blows from right to left. Here it blows from left to right, and somehow in the middle the two jets mix. So this is where mixing occurs. That's mixing layer. So therefore, we will break this into the following regions. So that will be region A, that will be region C, and this will be region B. Because individually these are straight line profiles, we will end up with a problem which I just described. Trivial solution. Okay? So it does not look like anything can happen here, anything of interest. But I will tell you, these corners here, they will play a role. And what actually happens at the corners? Just geometrically, what happens at these corners? So you have a profile like that, so the line is like that, and then at the corner, what happens? That was the slope, and that it became like that. So it suddenly changes, right? So du by dz is the slope of the velocity profile, and at the corners it will be essentially undefined, right? So it will be singularity. And if you try to differentiate it once again, if you would like to find the curvature, what happens at the corners? So curvature is the rate of change of the slope. How quickly does it change? So it was like that, and all of a sudden it is like that. Over what distance does it happen? It was like that, and all of a sudden like that. How long does it take to do that? So what distance do you need to travel to come from this and to this? 0. It's instantaneous change. Remember, the rate of change derivative is defined by the change over the distance at which it occurs. But the distance is 0. So therefore, curvature is infinite. It's singularity. Okay? That's what that means. And we will see how that singularity plays a significant role, because the solution, the true solution of this problem, is by far non-trivial. All right, here we go. So, but the point I would like to make before I will ask you to do the algebra is the following. At this singularity, we actually have to somehow solve the equations that contain singular points. And we cannot really jump over this singularity. We can approach this singularity from one side, and we can approach it from the other side, but we can go from one region to another without experiencing that sudden change, infinite change, right? Infinitely fast change, and that is unphysical. So in reality, this flow will not exist because we will see that the viscosity will always make a smooth transition. But at this stage, we do not consider viscosity, so therefore that's idealization. So what we will need to do is to use some sort of physical regularization approach. And our equation is written for, in terms of stream function, and it is written for stream function, psi, right? But in the original problems, what variables, physical variables, do we have? We have the velocities u and v and pressure, right? So now let us think about it. Can velocity jump? So we have two layers. One moves with this speed, the other one stays still. So something like that. In reality, is it possible? So one layer is stationary, the other one moves just straight behind, along it. Is it possible? What will you experience in real situation? It stands still, and I try to push my hand along it. So, and what do you feel when you do that? So you will feel pressure, and if you're riding a bicycle, a bike, and you're on a highway and you come off your bicycle or motorbike, what will happen? Your skin will be left on the ground, right? Right? And you will get burns. So the skin will actually burn because of friction. So, but we consider in the idealized situation when friction is not there. So therefore, in principle, velocity can jump. So this layer is stationary and the layer next to it is already moving because there is no friction, there is no interaction between the two. Okay, so that's our model. So therefore, we can imagine that things like that are possible, and we might even have like sort of jumps. So we have velocity like positive velocity at one point, and next to it the negative velocity straight away without even transition region or this transition region. So one leads to velocity region jumps into or changes suddenly into another. So for example, here velocity is positive, here velocity is negative, so it goes like that. Okay, so it is possible. It is possible if friction is neglected. But we also have pressure. What do you think the condition for pressure should be when we cross this boundary? So this is a singularity. So when we jump from here to here, when we cross this boundary, what do you think? So this is the boundary. And what do you think the pressure here and the pressure here should be? Physically. So this is the boundary. There is pressure here, there is pressure here. The boundary is not made of steel. It is not made of stone. It's just fluid surface, interface between two layers. There is nothing solid there. So there is a pressure here, there is a pressure here. What can you say about these two pressures? The velocity here and the velocity here are different. What about the pressure? I rephrase the question. Is the pressure the same or is the pressure different? Can it be different? Can it be different? So if it is different, so different, if we have equal velocities. Well, I will just restate the problem differently for you. So equal velocity, but one is left without going to the left, the other one going to the right. So velocities are equal, magnitudes of velocity are equal to. So don't bring in Bernoulli's effect here or Venturi's effect here. It's not going to work, right? So I eliminate that. So what's the pressure on top? What's the pressure on the bottom? Can it be different? Why? Yes, the answer is they must be the same. But the question is why? What if they are not the same? What will happen? If the pressure here is not the same as the pressure here, remember this is a thin layer, infinitely thin layer, so there is no distance over which this pressure changes. Which means that if there is any pressure difference, it will occur over zero length. What can you say about pressure gradient in this case? Infinite. But what is pressure gradient? Pressure gradient is physically, what does it lead to? What is it? Pressure gradient. Physically, yes, it is. Well, algebraically, it is a change of pressure with distance, yes. But what is physical? What is physically? What's the physical consequence of existence of pressure gradient? It's a force. Pressure gradient is the force. If the pressure gradient is infinite, it means that we have infinite force. If we have infinite force, then what? According to second Newton's law. We have infinite acceleration. So your fluid will just fly away instantly, right? So if the pressure here is large, the pressure here is smaller, there is a pressure gradient, and this occurs over a short distance, you have a shock wave. Explosion. What happens in explosion? Well, everything is destroyed, so we cannot have a flow like that. So therefore, physical condition is that even though we can imagine two layers sliding with respect to each other, across the layers, the pressure must be continuous. You cannot afford any non-zero pressure difference over infinitely thin layer because it will be equivalent to explosion. Okay? That's the physical interpretation of the fact. So mathematically, that means that if we evaluate pressure here and evaluate pressure here, they have to match at the border. At this level, they have to match. And I made the problem is a little bit simpler, so I remember we had the z equals 1/2 and -1/2. I made it just simpler for you because I would ask you to do some algebra for me. 1 and -1, okay? And I also chose the magnitude of velocity, -1 and +1. So everything is unit, just to make it easier for algebraically. Okay, so last thing I will do before I will ask you, and I'm not sure if we will have time to finish today, but if not, I will leave you with this overnight, and then tomorrow morning we will finish. We will start with the essential continuation of the tutorial. Okay. Pressure, 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 pressure. So let's look for our pressure. Where is that? So going back, going back, going back, going back, going back. Here. That's the pressure. That's explicit expression. So therefore, if we have stream function which is here, evaluated and here, then pressure will be evaluated according to this formula here and here. And the pressure here must be equal to the pressure here. This is called jump condition. Because velocity will jump from one profile to another suddenly, but pressure cannot change that rapidly. So therefore, it has to be continuous. So therefore, we will need to be able to evaluate the pressure at the top, the pressure at the bottom, and make sure that they are equal to each other. And the pressure is expressed here. So we have the explicit expression for pressure. Okay? So here it is. So now let's put it into algebra. So gradient of pressure, or pressure difference, is equal to 0 across the layers. So delta, this delta here, represents the difference between the upper value and the lower value across the layer. So above the border and below the border. So in that case, I will write an explicit expression. So there is a physical reason for that. So that's a physical condition, not algebraic, that's physical. Algebraically, how does it look algebraically? I will introduce a small change of notation. So I will introduce C, which is I sigma divided by alpha. It's because this combination appears everywhere, so, and it is a bit tedious to carry it through all the time. So I will introduce this notation, and I will rewrite the equations using this notation. So gradient of pressure then is, jump of pressure is 0, and that has to be equal to the jump over du multiplied by psi hat, so du bar like that, minus u bar minus c multiplied by d psi hat. Okay, and that must be equal to 0. So unfortunately I have to jump back and forth. So let me just show you where that comes from. So try to memorize what I've written here, and I'll go back and I will show you where it comes from. That's the expression. So therefore, what I need to do is to take this and evaluate it in the upper layer and the bottom layer. And that difference will have to be equal to 0. Is that clear? So, and that's what I have written there. How much time do I have? 7 minutes. 17. Okay, so at least I will be able to finish, and then I'll leave it all up to you, and I will be relaxing after that. All right, so here we go. The only thing, the only new thing which I introduced is this notation C. So we will see that that constant is actually not as a physical constant. It is called wave speed. So later on I will show you that it does make things move with a certain speed. So that particular thing. But for the time being, it's just an algebraic simplification. All right. So that means that if you look closely at this, you might notice that what we have here is actually a derivative in disguise. Okay? Are there any geniuses here who could see that without me showing? So there is a derivative sitting here. Right? How about if I say that P over U minus C U bar squared is equal to D of d means derivative, d by dz. Can you see that, or should I give you more hint? So unfortunately, giving you more hint means going back once again. So where is that? Where is that? Where is that? Where am I? So what you have here is function multiplied by derivative, and then function multiplied by derivative. So it looks like a product rule, except there is a minus sign. So whenever you have a product, instead of it has a difference there, not a plus sign, that means that there is a derivative quotient rule. So therefore it means that if we divide by something, it should collapse into a derivative. And that's exactly what happens here. So I'll let you to think about it, but the final outcome of this observation is that the pressure equation can be written like that. And if it is written like that, then of course we can formally integrate it at least once. So we cannot integrate the left hand side. The right hand side is easy to integrate. You just drop the derivative and that's it. But the left hand side, unfortunately, it contains unknown functions, so we cannot do it explicitly. But what we can do is consider the integral. Consider the integral between integral between z0 minus epsilon, z0 plus epsilon. I will explain what I mean by these epsilons. Limit as epsilon goes to 0 over which will simply be, of course, so hat So what I'm doing here, I'm integrating the right-hand side of this equation, right? That's what I'm trying to do. And if I integrate the right-hand side of this equation, then derivative will go, but what will happen there, I will have to evaluate this combination here at z0 plus epsilon and z0 minus epsilon, and find the difference between the two, right? So that's what this delta is. So what my integral here represents is essentially z0, where z0 is this corner point, for example. And we consider the integration between over this z0 region around the corner point from small distance above, or from small distance below to small distance above. That's what epsilon is. So therefore, I cut a small, very small region here around this jump point, this change of slope point, and I integrate over this region. Is that clear what I'm doing geometrically? So z0 is the location of this corner. And of course, we have two of them. So this will work for both of them. Z0 is location of this corner. And I integrate over that corner, but very close to that corner. That's what epsilon is. So in principle, I would like to make sure that this integration reduces to this region to, well, this limit reduces this limit to zero thickness. Is that? Yes, it is actually, I will just touch the, sorry, that's zero, I just touched it. Whenever I touch it, you see it leaves the mark on it. So it is Z0 minus epsilon, so it is below, slightly below Z0 and to slightly above. And if you integrate that, then you will see simply your derivative will be dropped and you will get upper value minus lower value. So that's what will happen. All right. So, if u minus c is not equal to 0, right? And we know that u minus c is not equal to 0, cannot be equal to 0, right? Remember, because c in potential has complex contribution, right? So therefore, the denominator is not equal to 0. So this doesn't have singularity, right? No division by 0 there. So then what we will have that the jump of the left-hand side must be equal to the jump of the right-hand side. So the jump over the right-hand side of this expression is already computed, right? Because it is just a derivative, so integral of derivative is just that combination itself. Okay? So that's what we have. What will happen on the left-hand side? So the jump on the left-hand side. So if you take this function and evaluate it slightly above and slightly below, this is not 0. And therefore, the variation of u is essentially the only variation which we will have there. So, that variation of u will become, if u is a continuous function, what will it become? It will become very small, right? So if we consider variation over a small region, over a small width, so variation of this quantity will be very small. What about variation of p? 0, it has to be 0, right? So therefore, this will be small. Variation of this, it's not necessarily 0, but it is small, right? But important thing is that this is non-zero. But this, variation of this, is definitely 0. So what's the result of variation, 0 variation divided by some non-zero variation? 0, right? So therefore, we get the so-called continuity or jump condition. So we will need to make sure that our system is complemented not only with boundary conditions, but also with the jump conditions, which are essentially conditions at these corners, at the transition points. Okay? That's what we are doing here. So therefore, remember my argument, initial argument was that if we consider linear profile with 0 boundary conditions, we will lose the whole thing. But it turns out that in this case, even though individual profiles are linear, this is a straight line, this is a straight line, and this is a straight line, but they are connected in corners. So therefore, we might have boundary condition here, we might have a boundary condition here, but in between those boundary conditions, we have another pair of conditions. And those ones are non-zero. they are jump conditions which need to be there to ensure that pressure variation is zero. Pressure has to be, variation must be zero. Is that clear? Just without algebra, just conceptually what it means. So when we have some sort of profile which is not given by a continuous line, not by a straight line, so by combination of straight lines, we have those corners. If we have those corners, we cannot jump over those corners. We have to make sure that we are going from one region to another in such a way that pressure remains constant, because if pressure starts jumping, we will have explosion, physical explosion, and that is not possible. To avoid that, we need to ensure continuity of pressure, and that means that we will have to enforce extra conditions, which we call continuity conditions or jump conditions, inside the layer. So it is not only boundary conditions which are outside of the layer that we need to take into account, but we also need to consider what happens at these corner points. Okay, I don't think we will go to any algebra today, but because we are all tired, so including myself, so therefore I will not ask you to do that. We will start with algebra tomorrow, so I'll do that. But I simply want to finish with a discussion of physical implications of what we are doing here, right? So physically, so in mathematical modeling, in applied mathematics modeling, we always need to make a reference to reality, right? If you do not do that regularly, so you pretty much will go astray. You will go on a tangent and will never come back. People will never see you. It'll just we will be in Lululand. So reality check. So and that where we are at now. So how much time is? 3 minutes. So I'm happy just to finish now and start tomorrow by stepping back a little bit. So just review what a few last things I did today, a few last things I mentioned here, right? From algebraic point of view, okay? But I'd like to do that afresh because you are tired, I'm tired, so it's probably a good idea for us to just to stop on this qualitative note and start with algebra again tomorrow when we are fresh.